this one's really more of an overview because a lot of people, we sit up here and talk about sanitizers and we don't really, you know, that was it as far as the Produce Safety Alliance curriculum goes. We don't really tell you how to use sanitizers or what's important with sanitizers. So let's talk a little bit about that. I'm going to train you on how to use chlorine, the metrics that are important if you're using chlorine, and then also one other sanitizer, proxyacetic acid. Does this mean these are the only two chemicals you can use to sanitize surfaces? No, you definitely can use others. These tend to be the two most frequently used. That's why we focus on those. Both of these can be used in organic production as well, so that's another place where they check off. So some commonly used sanitizers are chlorine, chlorine dioxide for larger operations, it's actually a gas that's produced, proxyacetic acid, and then ozone. So chlorine dioxide and ozone tend to be more commonly used in larger scale facilities, and that's why we really tend to focus on chlorine and proxyacetic acid. Now chlorine, we've probably are very familiar with. What's an example of chlorine? Yeah, bleach. Bleach is an example of chlorine. So bleach is sodium hypochlorite. If we've ever had to maintain a pool, we're using the powder form of hypochlorites and calcium hypochlorite in that tablet or pellet form or powder form. Proxyacetic acid is a liquid. These are a couple of trade names right here that are commonly found out on the market and that a lot of produce growers use. So there is what I call the ever-expanding list of chemical du jours. And chemical companies are a lot like companies that make anything else that's patented, protected. They're always coming out with a new formula. So they always have something new to sell you if you're working with a representative. And it's important to know that you don't have to change just because there's something new on the market. Because in reality, chlorine's been used for decades. And guess what? It still works very well if you're willing to deal with some of the metrics that are there. So the thing that we always tell people is if the product has been approved by the EPA. The EPA actually approves all sanitizers for efficacy. So you actually have to have an EPA label, and it has an EPA number associated with that label. And it's important that you never use a chemical that has not been approved. And again, even if it has been approved, there's going to be a maximum level that you're able to use it at. So that is key. A lot of times people will try and make up their own concoctions, and I tell them indefinitely, like, they haven't been approved as a sanitizer because that takes a lot of money, and you haven't done that, even though you may swear by them. So let's talk a little bit about chlorine. Chlorine in its liquid form comes as sodium hypochlorite. It is going to be at 5 1/4 all the way up to 12.5%. Calcium hypochlorite, again, is for larger scale systems, and that's typically going to be either in a powder or tablet form, and it comes at roughly 68% concentration. Why do we use chlorine? Well, it's cheap. And at the end of the day, you're always looking for something that's fairly inexpensive to get the job done. It can also effectively reduce pathogens in dump tanks and hydrocoolers as well as on food contact surfaces. So a lot of times we're actually using it for dual purposes within the packing house. It can also reduce the transfer of decay organisms to healthy fruit within that washing system or on other food contact surfaces. And really where it works the poorest is trying to kill existing pathogens on fruit. That's why I said with that tomato that may have had bird poop on it, leave it out in the field because you can't undo that. These sanitizers really aren't, even if you're washing that fruit really well, you're not going to kill whatever happens to be in that on the fruit itself. There are several things that impact chlorine's activity, and it's one reason why a lot of people don't like to manage it. Water pH is one area. You have to have roughly a pH of 6 to 7 to get the chlorine in the correct form of hypochlorous acid. We'll talk a little bit more about that in a second. Concentration Again, the more you have, the faster it kills, but there's always a maximum use level on that label you have to abide by. Contact time, again, the longer the contact, the more inactivation you tend to get, but roughly after 5 to 10 minutes, that really stops. So again, really where contact time comes into play, if the label says 2 minutes, you have to actually allow that sanitizer to contact for 2 minutes. This is really important, especially if you're using sanitizers for cleaning equipment. Organic matter in the water is one of the biggies with chlorine. Again, we have to make sure that we have chlorine in roughly a clean environment for it to be able to work. Water temperature, typically the warmer the water, the better it works, but once you get above like 160, chlorine gas starts to evolve out of the water, and it's going to be going into the atmosphere around you. That's not good for you to breathe in, so it's all within a relative balancing act. We don't want the water to be too warm. Again, the type of pathogens, something else to consider. Chlorine may not be equally effective for all the bacteria, the viruses, and the parasites out there, but generally speaking, it works relatively well across the board. So when we put chlorine into water, we call that chlorine dosage. So I've sat there and I've put in some bleach into my water that I'm going to be using as a sanitizer. What happens first is that you'll have chlorine interacting with inorganic matter in the water. So that comes through minerals. If you have really hard water, you're going to have what they say a high chlorine demand. And essentially you're going to be making salts at that point, right? So you're going to have the chlorine interacting with those minerals and making salts. Guess what? It's not going to kill bacteria if that's your goal. What we have remaining is total residual chlorine. So a lot of times if we're buying test strips, we'll be able to buy test strips for total chlorine and then free chlorine. So what's the difference between those two? Well, for total chlorine, we have two parts. There's combined residual chlorine, and that's essentially whatever interacts with organic matter. So if we have soil or plant residue in that water, then it's going to definitely form combined residual chlorine. The remainder that we have is called free residual chlorine, and that's what's actually able to kill the microorganisms that we're targeting. So if we have a choice to make between monitoring for total chlorine and free chlorine, we always want to pick free chlorine. So since free chlorine gives us that antimicrobial power, that is what we're always going to monitor for. However, that free chlorine has to be in the correct form, and this is influenced by pH. So once, say, bleach goes into the water, once it's around a neutral pH of about 7, it forms what we call hypochlorous acid, and this is what's going to kill bacteria. However, as we shift that pH to an alkaline range, so as we get above 8 or so, it forms what we call a hypochlorite ion. That is not going to inactivate bacteria. So in addition to monitoring for free chlorine, we also have to monitor for pH. And really we're targeting a pH of roughly 6 to 7 because that's where we're going to get good activity of our sanitizer. This is just showing that, again, once you get above pH 8 down here at the bottom, you have very little chlorine in its active form. And as you move to pH 9, there's roughly none left in that form that's actually going to kill bacteria. So a lot of people like to add chlorine in the glug-glug method. And this shoots them in the foot because guess what? The more chlorine you add, the more you shift the pH to an alkaline range. So you can add the correct amount and have 180 parts per million, and then add twice that amount, or 10 times that amount, shift the pH very alkaline, and still have the same amount of effective chlorine there, and you're only costing yourself money in addition to adding the chemical at too high a concentration, I guarantee you above what's allowed on the label. So in example 1, we add enough to have 200 parts per million at a pH of 6.5, and we get 180 actually in free form. But when we add 2,000 parts per million, so 10 times the amount, we only have 200 parts per million in the correct form because we have too much there and we have our pH 2 alkaline. So here's that example where we have 200 parts per million yielding 100 parts per million free chlorine at pH 7.5. Here's 200 parts per million yielding 180 parts per million at 6.5. And then here's 10 times that amount down here on the scale where you're only still getting around 200 parts per million at 10 times the cost to you. When it comes to reading labels, they can be tough. And a lot of times the labels don't actually come on the material you're buying. So you actually have to work with your supplier to get that label, and you always want to make sure you have that on hand, especially if you're being audited or being inspected for some other reasons. So on this label, we're not selling this product by any means, but this is a calcium hypochlorite briquette. It tells you right here what the concentration is. On the label, it also has what its use is for commodity fruit and vegetable washing. Separate to this, so it also have use as a sanitizer for food contact surfaces. For the washing, it tells you exactly how much you add and what the contact time needs to be. So these are two things we're always keeping in mind when we're looking at any sanitizer. A lot of times what you'll notice for food contact sanitation, separate from washing, is that you'll actually have much higher concentrations. So where you have 100 to 150, you may have like 200 parts per million for sanitizing. This is just a basic dosing scheme where it tells you how many briquettes to add to get the appropriate concentration based upon how much water you're working with. We also need to monitor, and essentially we use test strips for this. So our test strips are basically going to give us a color change as we increase in concentration. So it's going to be a crude measurement, but we're going to know ballpark where we're at. Our test strips are always going to need to be for free chlorine, and we're also going to have to check for pH, though, to make sure that we're in that 6 to 7 range. You can use more automated systems using oxidation reduction potential, and just know that that's something you can do as you start to grow if you want to have a continuous measurement system. Proxyacetic acid is our other compound that we commonly use. Proxyacetic acid is always easy to pick out because it smells like vinegar. So that's one of its telltales. And the reason it smells like vinegar is because you have proxyacetic acid in water generated in addition to acetic acid and hydrogen peroxide. Now, while these are all things you've heard about, you may think, oh, well, that sounds way more mild than using bleach. This is in a very concentrated form, and you still need to have appropriate personal protective equipment in place, so definitely wearing gloves, having aprons on to protect yourself, because this will burn you all the same, even more so actually than bleach will. 24 to 85 parts per million proxyacetic acid is a common use level for our post-harvest water. Additionally, you may get slightly higher concentrations for sanitizing equipment and things along those lines. Compared to chlorine, we a lot of times call proxyacetic acid PAA. It's not as impacted by organic matter, which is a big advantage. And it retains its activity over a wider pH range. On the downside, it is more expensive. However, for most of our growers, a 2.5 gallon tote will actually last them the entire season, especially even using it in their wash water in addition to as a sanitizer for those food contact surfaces. This 2.5 gallon tote, though, will cost you around $150 to $180. This product is Sanidate 5.0. That means it's a 5% roughly concentration of proxyacetic acid. You can buy in a more concentrated form if you have a larger operation, but typically 5% concentrated, a good concentration for most small and medium processors. So again, with the PAA label, this is blown up from their label. It says, for the sanitation and disinfection of hard, non-porous surfaces. It also goes into the treatment of water for washing produce. It goes through the concentration right here. So I said it's 5.0, so it's 5.3% peroxyacetic acid. This is specifically where they go into the treatment of fruit and vegetable processing waters. They have an exact equivalent for sanitizing food contact surfaces, and essentially it tells you what concentration you need to have of that sanitizer and what your contact time needs to be. For peroxyacetic acid, essentially titration solutions many times are used for PAA because we have a lot of compounds within that water, and our titrations are typically a little bit better at differentiating those. We can still use test strips, but you have to be very mindful of reading those test strips within the time limit denoted on the label. So we'll get an example here in a second of what that looks like. Again, when you're running your multi-million-dollar packing house, you can also have highly automated systems for peroxyacetic acid dosing and monitoring. So, in summary, sanitizers must be approved by the EPA for use on food contact surfaces. Sanitizers must be monitored for concentration and contact time to be effective. And you must read the label to know what you're shooting for concentration and contact time. So you smelling it is not going to be the good metric for you at the end of the day.